Bit of a rough start. um, Good afternoon and welcome to NOAA's National Ocean Service Science Seminar Series. If you are interested in receiving NOAA's weekly seminar list, just email me at tracy.gill@noaa.gov or Google NOAA Seminar to find out more. And so today is the sixth in an 8-part climate series co-hosted by Katie Reeves of the U.S. Global Change Research Program and myself, Tracy Gill from NOAA. I'm going to provide some logistics about today's seminar, and then Katie will introduce this seminar and the speaker. We have switched to Adobe Connect for this seminar series to accommodate more participants and to record the seminar. The recording and a PDF of the presentation will be available a few days after the webinar, and we will post a link to the recording and the PDF in the chat box. Feel free to ask questions in the chat box, and we will try to respond as soon as they come, but we may need to wait until the end. People in the room, please sign in and silence your phones. And now Katie is going to introduce our seminar and presenter for today. Katie? Hold on, Katie. We're not hearing you. That's my fault. Okay, Katie, go ahead and try again.
Okay, can you hear me now?
Yeah, sorry about that.
Great. Oh, it's no problem. So good afternoon, everyone, and thank you for joining us for the 6th installment of the Climate Science Special Report webinar series. I'm Katie Reeves, the Engagement and Communications Lead for the U.S. Global Change Research Program, or USGCRP. The Global Change Research Act of 1990 mandates that USGCRP assist the nation and the world to understand, assess, predict, and respond to human-induced and natural processes of global change. One way that we do that is through the development of a mandated quadrennial national climate assessment. The Climate Science Special Report, which is the focus of this 8-part series, represents Volume 1 of the 4th National Climate Assessment. It was released in November of 2017. The report assesses the science of climate change with a focus on the United States and serves as the foundation for Volume 2 of the assessment, scheduled for release late this year, which will look at climate-related impacts, risks, and adaptation across the U.S. You can read and download the Climate Science Special Report at science2017.globalchange.gov, and it should also be in the chat box. Today, I'm really pleased to introduce the causes and consequences of a rapidly changing Arctic with Dr. Patrick Taylor. Dr. Taylor is a research scientist at NASA Langley Research Center, where his research focuses on understanding the mysterious life of clouds. He's a member of the Clouds and Earth's Radiant Energy System Science Team, leads the Climate Processes and Diagnostics Research Group, and serves as a member of the Science Directorate's 10-year Planning Committee as co-lead for the Radiation Budget Focus Area. Dr. Taylor received the 2012 Presidential Early Career Award for Scientists and Engineers, a NASA Early Career Achievement Medal in 2013 for his research, and in 2015 he became a National Academy of Sciences Kavli Fellow. He was appointed to Virginia's Climate Change and Resiliency Commission by former Governor McAuliffe, is a member of the Science Working Group for the Old Dominion University-led Sea Level Rise Initiative, and somehow also found the time to be lead author on the Climate Science Special Report. So with that, thank you, Dr. Taylor, for joining us on today's NOAA Science Seminar. I'll turn it over to you.
Okay, Patrick, we can't hear you. Let me see what's going on.
Can you hear me now?
Yes.
Figured that was going to happen, but.
Thank you.
No problem. So thank you for that introduction. So I'd like to start by discussing the vote. No, not the election that's coming up in November or even the one that happened a few years ago, but rather I want to start with a vote that happened exactly 2 years ago today. In fact, on August 16, 2016, a contentious vote occurred in Alaska. It was the village of Shishmaref, which is in northern Alaska, located on Sarachef Island, just into the Chukchi Sea. This village voted. The vote was extremely close. It was 89 to 78, and it had a 99% turnout rate, in fact. Incredible turnout rate. Ultimately, the vote represented the decision of the village to relocate, effectively surrendering to climate change. Here's the location of the village. The decision by Shishmaref was effectively forced by coastal erosion. Sarachef Island has lost nearly 3,000 feet of land of coastline since 1980. That's about losing a football field's worth of land every 3 years or so. These rapid changes that we've seen in the Arctic particularly the ones in sea ice, including both the reduction in extent as well as the lengthening of the sea ice melt season, has allowed the wave action from the strong storms in the Arctic to literally consume the coastline, which has served to destroy homes as well as the village's infrastructure. These changes in sea ice have also left the people, not just of Shishmaref, but of the Arctic, more vulnerable by shortening hunting and fishing seasons, for they rely on the extensive sea ice in order to hunt for food and to fish to make it through to have food for the winter. Now they must wait for later in the fall so that the ice freezes, so that it'll be safe enough to walk on. This story of Shishmaref is not an isolated event, but rather it represents an anecdote, and it represents a story that's happening all across the Arctic in response to the rapid changes that we're seeing. And this story really highlights 2 points that I'd like you guys to take away from my presentation today. First, it's that the Arctic climate is changing now, and it's affecting natural and human systems now. This is not a far-off threat. People, and in fact Americans, are poised to become climate refugees. And secondly, these circumstances highlight the need for better and continued information, data, and models so that we can plan and prepare as well as improve our projections of the climate changes that are happening in the Arctic. This is so that decision makers can have the best possible information in order to make their decisions. The improved data, models, forecasts, and the projections, in this case, in the case of a more accessible Arctic, a warmer, less icy one, is becoming more important, not less important. The opportunities in a less icy Arctic are in fact many, and I'll touch on some of those throughout my presentation, but also they come with unique challenges and threats. Operating in the Arctic really is no less treacherous than it used to be. And as environmental scientists, our work does affect people's lives. And in fact, our work, taking the data, improving the models, doing the science, is more important now than ever. And that fact really motivates me every day I come into work, with the understanding that something that I can learn today may improve somebody's life or save a life even tomorrow. So again, my name is Patrick Taylor, and I'm a research scientist at NASA Langley Research Center, and it is my pleasure to be with you here today and to share the findings and to share the key findings from the Arctic chapter of the Climate Science Special Report, which was so nicely introduced a few minutes ago. So I'll start by talking about the key findings from the Arctic chapter, but then I'll move on. I'll take this opportunity to share a few things about why the Arctic is changing so fast from my personal research, and then I'll close the presentation by discussing some of the projections that we expect going on and describing some of the consequences for this rapidly changing, less icy and warmer Arctic that we expect. A better understanding of the predictions of climate are important because what we are coming to realize, and what I'll be honest that I haven't realized for as long as you think I would with a PhD in climate science and meteorology, but these the systems that underpin our society: food, energy, water, economic systems, security systems. They're extremely climate vulnerable, and our understanding of the climate and understanding of what's going to happen in the future helps make these systems more secure and more resilient going forward. Because of these important links between climate and our everyday life, it makes sense to periodically take stock of the impacts of climate variability and change so that we can assess risks and make plans going forward. And this, as Katie mentioned, is part of the point of the National Climate Assessment. So again, the National Climate Assessment is this quadrennial assessment that is mandated by Congress, that I had the honor of taking part of. In fact, as I was mentioned before, I was the lead author for the Arctic chapter, which I will discuss today. But I wanted to share a few of the stats with you today to give you an overview of this report. It is, in fact, the Climate Science Special Report is an authoritative assessment of the science of climate change in the U.S. It is 470 pages with 63 key findings, and clearly there's not enough time to go through all of them today, and that's why it's an 8-part seminar series. But also want to point you to the fact that this report was in fact reviewed 6 different times, both inside the government as well as public comment period and a review by the national academies. So it certainly is a thoroughly vetted report. And I do have to say that the process in putting together this report, it was extremely well managed by the USGCRP, in my opinion, and we really couldn't put it together without put the whole thing together in the timeline that we did without the vital help by the technical support unit and others supporting it. So, as the lead author for the Arctic chapter, I'd like to share with you now our key findings from that chapter. So, but first, let me step back and paint a picture of the Arctic and a bit what it was 40 years ago. 40 years ago, the Arctic was this region kind of encased in snow and ice where multi-year thick sea ice was everywhere pretty much. And it was at that time, 40 years ago, that some climate scientists, Manabe and Weatherald, made some climate projections that suggested the Arctic would be more sensitive than any other region to increased carbon dioxide. The findings of Chapter 11 and the science that's summarized in Chapter 11, the Arctic Changes chapter of the Climate Science Special Report, documents many recent observed and in several cases unprecedented changes in the Arctic climate system that in fact verify this prediction that the Arctic would be more sensitive than any other region on Earth. As part of this chapter, again, we arrived at 5 key findings about various aspects of the climate system, but these key findings relate primarily to what we've observed over the last 30 or so years in terms of the Arctic and the changes. I'd like to start with, at the beginning, with key finding 1, but it highlights a very often cited aspect of the Arctic and Arctic climate change, which is the fact that the Arctic temperatures are, especially over the last 50 years, have warmed at more than twice the rate as the rest of the globe. This plot here showing the zonal average temperature anomalies from the NASA GIS temperature record highlights this, where you can see on the far right, top right portion of this, the red and orangish colors in the Arctic, showing the Arctic is warm much faster than the rest of the planet. But in particular, if we focus in on Alaska and in specific surface temperature sites in Alaska, we see that Alaska as a whole is warmed by about 0.8 degrees Celsius since 1981. But then if we look at Yukvik, formerly known as Barrow, Alaska in particular, and we look at the fall months, we see that since 1979, Yukvik is warmed by 3.8 degrees Celsius in September, 6.6 in October, and 5.5 degrees Celsius in November. So this is showing more than 1 degree Celsius warming per decade in these months at this location. So certainly the warming in the Arctic is at least twice as fast as the rest of the globe, and in particular regions of the Arctic is proceeding much more quickly than that. So the reason we start with surface temperature is because the temperature, surface air temperature is tied to, it's an intuitive variable first that we all kind of have a sense for, but also the temperature affects many other processes and properties of the Arctic, in particular its frozen state. So not just the surface air temperatures warming, but the ground temperatures are on the rise as well. And this is affecting the permafrost characteristics, both in Alaska as well as across the Arctic. And they're responding to both the increased temperature as well as the reduced snow cover that we've seen. Permafrost is defined as ground that has been frozen for 2 or more years. The reason that we care so much about permafrost is that frozen in that ground is a significant amount of organic material, meaning dead plants and dead animals, that as the ground warms up and begins to thaw, that organic material now becomes susceptible to microbial action and decay. That microbial action then releases both carbon dioxide and methane during that decay process, which, as we know, is an additional climate forcing. And this is the elements of this are spelled out here in our second key finding, where we highlight the fact that the permafrost is in fact warming, where we see trends in the permafrost temperatures anywhere from 0.2 to 0.7 degrees Celsius per decade. And these are at various depths. So to get these temperature records, which in the plot here span back at a few locations to 1978 or so. They're boreholes that are actually drilled in the ground, and so these are temperatures from anywhere, depending on the site here, anywhere from 12 meters at depth, 15 meters to 20 meters at depth. These temperature changes are happening. And what we find here is that the places that are cold are actually warming a little bit faster than the ground temperatures that are a bit warmer. So overall, our key finding highlights the fact that the release of carbon and methane from a thawing permafrost, this is termed the permafrost carbon feedback. And while we have high confidence that this feedback is indeed positive, the magnitude of this feedback is a bit unclear what it is. The best estimates that we have is that by the end of the century, by 2100, the additional release, the additional warming due to the permafrost carbon feedback could be anywhere from 0.1 to 0.5 degrees Celsius. But what is clear from this feedback and this interaction is that these emissions that are associated with thawing permafrost could indeed compromise our ability to limit temperature increases to any number that we pick, whether that's 2 degrees Celsius or otherwise. So moving from kind of the land temperatures to the broader Arctic cryosphere, our third key finding in the chapter highlights kind of all of the cryospheric changes that we're seeing. And in this animation, what we're looking at are the changes in September sea ice from 1984 through 2016. And what we highlight in the chapter, as well as what this animation hopefully shows, is that the character of Arctic sea ice indeed has changed dramatically over the last 35 or so years. And our third key finding highlights the fact that not just the sea ice is changing, but also the mountain glaciers and the ice sheet as well. So I'll play this animation again so you guys can look at it again. But what you're seeing here are passive microwave satellite retrievals of sea ice. The colors, any color means represents the aerial extent of the sea ice, but the specific colors from light gray to the brightest colors represent the first year sea ice to the oldest sea ice. So again, the oldest sea ice, the sea ice that is more than 4 years old, is shown in the brightest white colors here. What you can see from the beginning to the end of this is that the total extent of sea ice, the aerial extent of sea ice over the time period has declined by by over 40%, which is equivalent to about 3 million square kilometers. To put that into perspective, that's similar as the land area of Alaska, Texas, California, and Montana combined. Those are the four largest states in the U.S. in terms of land area. And just to put that into perspective, because something that I didn't truly have an appreciation for until I looked up that statistic, is that Alaska is actually 3 times the size of Texas. So in fact, of area of sea ice lost, it's about 4 times the size, the land area of Texas in sea ice extent. One more look at this, and if you focus on the changing in the colors of the September sea ice extent, you can see that there's a large change from much brighter white colors to much duller gray colors, marking the change in the age of the sea ice. So the sea ice, in fact, has become much younger in this time. If you comparing March 1985, the oldest sea ice, more than 4 years old, accounted for roughly 16% of the total ice cover, whereas now in March 2016, it only accounts for 1.2% of the total ice cover. The reason we care about the age of the ice is because it corresponds directly to the thickness of the ice. And so that then thickness times the aerial extent gives you sea ice volume. Sea ice volume is much more, is probably a better indicator of Arctic climate change, specifically the impacts of Arctic change on the flows of energy around the Arctic, as the volume change corresponds directly to the changes in energy that we've seen. And the volume declines, according to the biomass data set, which is the best data set we have with the longest record of volume, indicates that volume has declined by on the order of 70% since 1979. So in addition to these changes in the just the extent of the sea ice, but the Arctic sea ice melt season has lengthened significantly since 1979 as well. In particular, if you look at some of these brightest orangish colors here off coastal Alaska, that indicates that the melt season of sea ice is lengthened by some 20 to 30 days per decade. And so if you take the top end of that, the 30 days per decade trend, in some of these regions of coastal Alaska, we're seeing up to 90 more sea ice free days annually. So linking that back to what Shishmaref, the village of Shishmaref is seeing is that it's in fact these many fewer sea ice free days that are allowing the coastal erosion to occur and their village to literally being swept into the ocean. And so not only is this change in the sea ice melt season really important for some of the impacts of Arctic climate change on human systems on us, but also it has significant impacts for the physical climate system that I'll talk about a little bit later in terms of explaining or impacting why the Arctic is in fact changing so quickly. Another part of this key finding, I know key finding 3 seems to go on forever, but another part of this is that we've seen dramatic changes as well in the Greenland ice sheet, particularly at its margins, which will become evident as we go forward in this animation. So this is data from NASA's GRACE mission. And on average, since May 2002, we see, which is when this record began, we see that there's an average of 281 gigatons of ice mass that has been lost from the Greenland ice sheet per year. That is enough water to fill more than 140 million Olympic-sized swimming pools, in fact. And so if you put those Olympic-sized swimming pools kind of next to each other, you get, that's about the land area of New York State. So that's a very large Olympic-sized swimming pool, in fact. Before this, the GRACE observations, it's interesting to note that the science community consensus was that Greenland ice sheet wasn't contributing very significantly at all to global sea level rise. However, since over this time period, since 2002, what we know now is that this Greenland mass loss is accounting for about 25% of the global rise in sea level. In addition to the Greenland ice sheet, ice in the mountains is also, mountain glaciers are also in decline. Here is an example of just one such mountain glacier from Alaska, where these two pictures are taken by the USGS, the U.S. Geologic Survey, for their repeat photography program. And this is the Muir Glacier, and what you can see here is the difference between these pictures from 1941 through 2004 is that the Muir Glacier has retreated some 4 miles to the northwest here, almost out of view in this photograph. The annual average mass loss from glaciers Arctic-wide has decreased every year since 1984. So if you take up all the glaciers Arctic-wide, every year since 1984, it's been there's been a loss of mass. We haven't seen a gain in mass in that time, with especially significant losses occurring in Alaska over the past several decades. And so it's virtually certain that Alaskan glaciers have lost mass over the last 50 years. So I'd like to anchor at this slide for just a moment and use these images to kind of discuss the role of human activities in driving these changes that we've seen in the Arctic. And this is the topic of the 4th key finding in our chapter. And this key finding states that it's very likely that human activities has contributed to the observed Arctic surface temperature warming, sea ice loss, glacier mass loss, and northern hemisphere snow cover decline. Now, this key finding may not seem new to most of you if you're familiar with some statements from the IPCC made over the, for instance, in the IPCC AR5, the 5th assessment report. It sounds very familiar. However, what we were able to do in this report, supported by new science, new research that has been published since the 5th assessment report, is ratchet up the confidence and likelihood statements here to include very likely and high confidence in that. One of the particular emerging science that contributed to this was the science of extreme event attribution. It's been served as an important justification for this, and what it's indicating, what the science is indicating, is, for instance, that the record September sea ice minimum in 2012 it would not have happened. It could not have happened in the absence of a human influence on Arctic climate change. So the final key finding for our chapter involves the linkages between the Arctic mid-latitudes, and this is an area really of active research and a lot of controversy, as I'm sure many of you have seen the articles about the potential for reductions in Arctic sea ice influencing colder outbreaks, in particular in the east coast of the United States. And so this key finding kind of spells out both sides of this. The influence of the mid-latitude circulation changes on Arctic temperatures and sea ice, which, as is stated in the key finding, the science indicates that there's high confidence that changes in the mid-latitude circulation are in fact causing warmer temperatures in the Arctic and are influencing sea ice. And I'll show some results from that later on here. However, the opposite, whether the Arctic is influencing mid-latitude weather and in particular extreme events, is something that we've assessed that it's low confidence whether that is happening. And there's low confidence in what the mechanism may be for that. So this is certainly an area of active research and an area that deserves a lot of attention, and it was in fact elevated to a key finding specifically because of the potential for significant impact on the U.S. if there is this link, if the changes in the Arctic are causing more extreme weather events in the Arctic, or excuse me, in the United States. So to summarize these key findings, what we see is that the Arctic changes have been rapid and in many cases unprecedented. And in my view, this begs several questions, considering what we've seen over the last 35 or so years. The first being, why are these changes happening? Why are they so fast? Do we expect them to continue going forward? And then lastly, what are the ramifications or consequences of these changes? So first, let's tackle why the Arctic is changing so fast. This property of the Arctic is given a name, and it's called Arctic amplification. So that's sort of the jargon that goes around for this. And it's actually a notion that was hypothesized by Arrhenius originally in 1896. So it's been around for quite a while. But we understand much more about the drivers and its structure now, much more than we did then. Shown here, what you're looking at here, are temperature trends in the Arctic from that add together the 5 different reanalysis data sets that we have, NASA, NOAA, as well as the Japanese JRA 55 reanalysis data set. And the temperature trends are broken out into the 3 different seasons. So we have December, January, February, March, April, May, June, July, August, and September, October, November. And what you see are a couple key features of kind of the nature of the warming pattern for Arctic amplification. We see first that temperatures have warmed much more poleward of 75 degrees north versus equatorward of 75. So again, Arctic focused warming. We also see that the warming is what we call bottom heavy, or it's surface focused. So you see the largest warming, which in some of these cases is exceeding 0.8 to 1 Kelvin per decade warming that we see close to the surface. And then lastly, we see that the most warming is in fact happening in fall and winter time. And so the reason I bring up these features of Arctic amplification and this nature of Arctic amplification is because these key features of Arctic amplification provide clues as to what the mechanism that's driving these changes may be. And in fact, a complete theory of Arctic amplification must be able to account for all of these key features. And so to explain these warming patterns, we really need to consider the energy flows and where energy is coming to and going to and coming from. And so energy, I like to think of it as the currency of our climate system. In fact, you can't, just like you can't buy or sell anything unless money exchanges hands, the temperature doesn't change and it doesn't rain unless energy moves around. The reason that the Arctic is warming faster than anywhere else, that means that it's accumulating energy at a faster rate than other places. And so this is why we look at and are studying the energy flows coming into the Arctic, as well as how energy moves around the Arctic. So to kind of a summary of all of the different processes, and I know this is a busy chart, and so I'll summarize some of the key ones in a minute here. But this is the reason why we are the importance of the energy flows argues for the importance of looking at all these different processes that are influencing Arctic amplification. So some of them in the peach arrows here are summarizing local feedback mechanisms, processes that are kind of local to the Arctic, which include sea ice loss, as well as changes in sensible latent heat fluxes, energy exchange with the surface, increased storage of energy in the ocean, as well as changes in clouds are all potential contributing factors to Arctic amplification, as well as in the purple arrows are summarizing the remote external forcing. So this is the transport of moisture and energy and heat by the ocean and by the atmosphere into the Arctic. One other really key piece of this story for Arctic amplification appears to be the seasonal exchanges of energy, whereby changes in energy that is stored, solar energy that's stored by the ocean in summertime is transferred into fall and winter, where it seems to be having a much larger warming influence. And that seems to be a very important transfer of energy for why the climate models predict such a large warming in the Arctic and why we're seeing such large changes. So just to highlight a few of these arrows in particular, I'd like to start with probably the feedback that most of you are most familiar with or have heard, and it's been the long-held reason that people argue for as the cause of Arctic amplification, and that being the ice albedo feedback. So what's shown here in this visualization is that ice is bright, it reflects a lot of solar radiation to space, and as sea ice melts back, it's uncovering a much darker ocean underneath. The darker ocean then absorbs the solar radiation more effectively than the ice does, and therefore that extra absorbed solar radiation, solar energy, can warm the surface. Warmer surface temperatures help to melt more sea ice, which helps to uncover more darker oceans. So this is this amplifying feedback loop that is driving some of the warming in the Arctic. And in fact, more than just this kind of cartoon of the process, we have data that actually verifies that this has happened over, since the year 2000. So this is NASA data, but what you're seeing here in the blue colors are the changes in sea ice fraction that we've seen over this 15-year time period in the bluish colors. And then in the reddish colors are from the NASA Ceres surface radiation budget data set, which is Ceres, CERES series, is the science team I'm a part of here at NASA. And what we're showing here is that exactly the places where sea ice has declined are the places where we've seen the largest changes in absorbed solar radiation. And so this is observational verification that the ice albedo feedback is indeed operating currently in the Arctic. The other mechanism the other primary mechanism that folks are arguing for driving Arctic amplification is what we call the remote mechanism, which were those purple arrows in the other chart. And this mechanism works by the winds carrying warm, moist air from mid-latitudes into the Arctic. And so here's an example from just this past February showing exactly kind of how this mechanism works. And so normally in February timeframe, the Arctic temperatures are very cold and hover close to minus 20 degrees C or so. However, the last 3 winters in particular, and some of them have made the papers, you've seen air temperatures at the North Pole surge above 0 degrees Celsius at certain times. And so here's one example of that just this past year, where on February 20th, the temperatures in Greenland not only reached 0 degrees Celsius, but stayed there for more than a day. In fact, then a few days later, and so, sorry, let me slow down, stop a second and explain the animation that you're looking at. And what you're seeing here is an animation of air temperature anomalies, where the reddish colors are showing you much warmer temperatures. And what you can see is the red blob here begins begins from farther south here over Greenland, and then moves in over the North Pole region. And this is the winds carrying those warm temperatures from more southerly latitudes into the Arctic. And something that I haven't really done before, that I guess this is an indication of the new technological age we're in, but I've never really referenced a tweet before. But here is a tweet from Robert Rody was showing exactly the hours above freezing that occurred in relation to this event at that yellow star that's marked there as the most northern station uh, in Greenland, Morris Jessup. And it shows during this event, the station accumulated 61 hours above freezing, which, if you look at this time series going back to 1980, the blue bars denote the number of hours above freezing between January through April, and this far exceeds anything that has happened since 1980. And in fact, it's not an annual occurrence where you have these many hours at this point above freezing between January and April. Um, and in fact, in particular, for a time at Morris Jessup, the temperature reached 6 degrees Celsius or 43 degrees Fahrenheit. And so I know that we have several colleagues, I do in particular, that they would call that shorts weather, which seems odd to be in the dead of winter at the most northern tip of Greenland. And so what this example is showing you is the potential. It illustrates the potential for this remote mechanism, this influx of heat and moisture into the Arctic, to really influence the temperatures of the Arctic and really change. And if changes in the frequency of these events occur going forward, this could influence how fast the Arctic changes going forward. So in an attempt, in some research, again, that I've been a part of, in an attempt to kind of put this whole story together, I have this series of bubbles that kind of put together both these local mechanisms, the loss of sea ice, with this remote mechanism, which is the atmospheric transport of heat and moisture into the Arctic. And so one thing we can agree on, while a agreed upon kind of complete theory of Arctic amplification is we're not there yet. However, I feel like we're close. But what we can agree on is that a lot of the changes in surface temperature in the Arctic come down to this term right here, which is the long wave downwelling radiation, which has been increasing in this time, and it's due primarily to a warmer atmosphere, a moisture atmosphere, and a cloudier Arctic. This increase in downwelling long wave radiation then results in warmer Arctic surface temperatures. And so we consider the local feedback mechanism, which again is tied to the sea ice itself. We see that a warmer Arctic results in less sea ice cover. Now, less sea ice cover then yields larger absorption of solar energy during summer, which is the SAF here is the surface albedo feedback mechanism. And then that results in more storage of heat into the ocean in summertime. That energy that's stored in the ocean, because of the phase change of the sea ice and because of the thermal capacity of the ocean mixed layer itself, that energy doesn't really warm that layer very much at all. It just stores that energy there. And then what that extra energy does, though, is helps to delay the fall freeze up of sea ice. And so as you delay the fall freeze up, this then supports this what's called H-flux here, which is it enhances the exchange of energy from the surface to the atmosphere. So now the less sea ice is able results in more energy going from the ocean into the atmosphere, which helps generate a warmer atmosphere and moisture atmosphere, and at times a cloudier Arctic atmosphere as well, which then increases long wave down, and then we have this feedback loop that occurs to help drive the warmer Arctic. From the remote mechanism here, what we see from our analysis is that we have an increase, the CMIP5 climate models, the coupled model intercomparison project climate models are showing this increase in atmospheric heat transport into the Arctic, specifically in fall time, which is resulting in a warmer, moister, cloudier Arctic atmosphere. And so what this shows is that there's a place where these two mechanisms, in fact, can interact with one another. And if something that I would like you to take away with today isn't necessarily whether the local or the remote mechanism for driving these changes are in fact more important, but the fact that their interactions are probably more important. And let me demonstrate that here. So there's been a number of studies that try to isolate the influences of sea ice versus the influences of atmospheric heat transport, the remote mechanism, on sea ice. And so what you're looking at here are three different plots showing sea ice concentrations at the end of the climate change simulation that are summarized in Yoshimori et al. 2017. The one on the left here are just summarize what the local mechanisms working by themselves do. The middle one is what the remote mechanisms, so the heat transport, by itself does. And on the far right, if you compare, what you can see is the changes, how much larger the reductions in the changes in sea ice concentration are when these two mechanisms are able to work together. So in fact, what the lesson to take away from this is that, if we're going to get some of the largest changes in sea ice concentration, largest reductions in sea ice concentration by 2100, you expect those to happen in climate models where these two mechanisms kind of constructively interfere and kind of amplify each other. And so one question is then what do these interactions look like? And so here's a study that I was a part of with a postdoc of mine, where we looked at this a recent Arctic sea ice growth season. So the 2016-2017 season, which you show on the black line here, is showing you the actual sea ice extent from the data from the passive microwave satellite data from the National Snow and Ice Data Center. And what's unique about this year is that it did end up being a very low, one of the lowest end of season Arctic sea ice volume and extents on record in March 2017. But what was interesting, if you look at the time series here, you see these plateaus where there were several periods during this time where the sea ice extent growth either was reduced, was much reduced, or even became negative, showing reductions in sea ice extent for small periods at times where you would normally expect there to be sea ice growth. And so what we were able to do is that all of these periods that showed the reduced growth were associated with events where warm, moist air from low latitudes was being moved in by the winds. And just as one example of this from November 17th, 2016, and this was an event actually that made, I believe, the Washington Post, where they talked about more than 40-degree warm anomalies and temperatures happening across the Arctic. And so kind of an anatomy of one of these events is that these arrows here are showing you the anomalies of winds at 925 hectopascals. And so we had strong winds here pushing warm, moist air from low latitudes into the Arctic. And this term has been called this event has been called a moisture intrusion. And this is generating these very green colors here are what are precipitable water anomalies, or so very high moisture contents, anomalously high moisture contents in the Arctic. And so this presence of moisture, in fact, increased the downwelling long-wave radiation into the surface. And then on the bottom left here, these magenta colors from the biomass data set, which is sea ice volume, shows a sea ice volume loss associated with this. This doesn't mean that the sea ice melted away, but rather that the volume, the thickness of the sea ice was reduced during this period because of the event, because of the increased downwelling long wave. So effectively, the event changed the surface energy budget at this time. And so this is just an example of how the remote mechanism, how powerful it can be, and how it could potentially influence the sea ice, because this case illustrates that moisture events can indeed slow the sea ice, but also the slowing would precondition the sea ice cover. If it resulted in a thinner sea ice cover, then it could influence how make the ice more susceptible to melt going forward throughout the next summer. However, it's important to remember that the atmosphere often messes with us and reduces the predictability of the end of summer sea ice extent based on what we saw in March, because this year in particular was a near record low sea ice extent, but was not a record low September sea ice extent. So natural variability in the atmosphere certainly reduces that predictability. So given some of these underlying mechanisms for Arctic amplification, what are the predictions going forward? And so I'd like to highlight a few of the expectations for how the Arctic will change going forward. And most of what I'll show you here is RCP 8.5, or the more or less business as usual scenario for the changes. Looking at the top panel of this here, the line plot shows each line is a different climate model from the CMIP 5 archive. And what's plotted here is the amplification factor. So that is the amount of warming that happened in each of these latitude regions divided by the global mean warming. So a way to look at this is that any place where there's a 1 on this, where the line crosses the 1, that means that that region warmed the same as the globe for that model. And so what you see here is that as we get into the Arctic here, the warming in the Arctic is amplified with respect to the global average in all of these models, anywhere from 1.5 times to as much as 3.5 times more warming. So if you take the nominal 3 Kelvin warming due to a doubling of CO2 that the IPCC that's in the IPCC reports, that indicates that the Arctic is expected to warm anywhere from 4.5 Kelvin to as much as to more than 10 Kelvin by the end of the century. And if you look at on the bottom plot here, showing you a different view of the vertical changes of temperature that we're expecting, and we see that the average over the entire ensemble is roughly about a 7 Kelvin warming polar to 75 degrees north. So a very substantial warming, again, more than double what we expect for the globe. So if we look at this spatially, what we find out is not all regions and times of year are warming the same either. We see that in this plot, we show the annual mean, and we have the winter anomalies and the sunlit season where spring and fall, or spring and summer are kind of lumped together because of the way sea ice behaves, because in the atmosphere, but then also fall time. And we see that the largest changes, largest warming are found in wintertime, but the bottom plot here is showing you the model differences. Something I didn't highlight on the previous plot is that, is the fact that not just is the Arctic expected to warm more than the rest of the planet, but the climate models, in fact, disagree more about how fast the Arctic is going to change than anywhere else. The models disagree more in the Arctic than any other region of the planet. And so we see that there are large warming that we find in wintertime, and particularly in the places where we are expecting to lose the most sea ice. So if we look at the sea ice projected losses, that's shown on this plot here, and we see that on the far top right panel, we see in autumn we expect the largest declines in sea ice, and these are shown are sea ice concentrations where some places are losing 65% sea ice concentrations across much of the central Arctic region. And we see that during wintertime, much of the loss is happening in the marginal seas or at the edges, and so this is to be expected. And what this kind of tells us is that, wintertime sea ice, while the Arctic is transitioning from what's more of what used to be multi-year ice to more of first-year ice, the ice is growing back every wintertime. But the end of summer sea ice extent is indeed in jeopardy. So we'll always have winter sea ice for the foreseeable future, but the summertime, end of summer sea ice is expected to get to very low values. In fact, if we look at sea ice in particular, and as we summarize in the chapter, we expect that the Arctic sea ice extent at the end of summer in September can reach essentially sea ice free in the 2040s is the expectation. And so what's interesting, and so this slide is comparing the different projections of the sea ice depending upon the amount of forcing in the atmosphere, where RCP 4.5 is a stronger, more CO2 in the atmosphere, a stronger forcing, climate forcing, whereas RCP 8.5 is a stronger forcing than RCP 4.5. But what is interesting to note, and if you look in the bottom left panels here, those are shown by the different colored lines, is that the amount of Arctic sea ice loss that we expect by mid-century is essentially independent of the forcing, roughly about the same numbers you get. But it's after 2050 where you can see the RCP 8.5 essentially melts away all September sea ice, and the other scenarios leave some sea ice essentially behind. Then you can see that summarized on the spatial plots here, where RCP 8.5 in September shows essentially 0 sea ice across the Arctic by 2100, whereas RCP 4.5 has very low concentrations, but still some sea ice. And so Since I'm sort of running low on time, I'll move to the consequences of some of these changes. And so again, the Arctic is changing fast, and we expect that story to continue. Um, and there are many consequences to that. Most of which I won't be able to cover here with the time that we have remaining. But one of those that we talk about in the report is the effect on wildfires across Alaska and the Arctic. Um, the warmer, drier Arctic that's expected and that's occurring is making the region more susceptible to wildfire. We found in the report and documented in the report that there have been increases in both boreal forest and, fires as well as burning of the Arctic tundra. These are regions where fires have been historically smaller or less frequent. And in fact, the larger fires have likely become more frequent since 1959. And in fact, human activities have also likely added to the length of the wildfire season, as well as increasing the risk of wildfires, of severe wildfires. Um, there's also several studies out there that indicate that by 2100, there's a possibility that the projected changes in the Arctic would lead to a transition into a fire regime that has been unprecedented, unseen in the last 10,000 years. And so the importance of wildfire is because not just because of the burning, but also the smoke and pollution that's emitted by the fires, as well as the impacts on biodiversity and vegetation type across the Arctic. In this changing Arctic, there are a lot of physical implications to the physical climate system, but there are also implications and consequences that extend to both the economics and national security and geopolitics. Let's remember that the U.S. is an Arctic nation. I find this is often an overlooked fact, but we are an Arctic nation. And therefore, the decisions that we make about adaptation mitigation, resource development, trade, national security, economics, transportation, etc., depend on the future Arctic climate. Economically, a warmer, less icy Arctic contains a significant amount of opportunities. We can explore new areas for natural resources, so oil and gas, natural gas exploration. A less icy Arctic invites new, shorter, more efficient shipping routes, cut down on time and fuel costs for shipping, specifically between Asia and Europe. Also, a less icy, warmer Arctic invites tourism into the Arctic, which can be another economic opportunity. But we must remember that with these opportunities, there are challenges as well. The Arctic, while less icy, still remains treacherous. It's still the same difficult environment to operate in. For instance, cold conditions with frequent fog, there's still significant potential for icing. Also, less sea ice. There's less sea ice, but not sea ice free. And therefore, that thinner sea ice, in fact, is moving faster, being pushed faster by the winds than thicker sea ice, and therefore increasing the probability of collisions with ships. Moreover, those strong winds are also, and less sea ice generate more waves, stronger waves as well, which can influence the navigability of the Arctic Ocean. And so one of the things that all of these potential challenges indicates is the need for search and rescue operations in the Arctic, which is a topic that was brought up by the Arctic Council, and an international agreement was struck on this in recent years to cooperate. So that's definitely good news. However, there's one other opportunity / challenge in the Arctic, in a warmer, less icy Arctic, and I feel like that's a bit the 500-pound gorilla in the room, and that's national security. Given these opportunities, new opportunities in the Arctic, there's a need for governance, for enforcement, and there's certainly a possibility for conflict and disputes. And the U.S. national security apparatus needs to be prepared for those potentials, including being equipped with the best forecast data and information possible. In fact, so I live in Southeast Virginia, and Naval Station Norfolk is I don't want to, it's one of the largest naval bases in the world. It might be the largest, in fact. And so we get a lot of U.S. Navy news coming across our newspaper. And in fact, just this past Sunday's paper had an article summarizing the plight of naval operations in the Arctic. The U.S. only has one heavy icebreaker ship that's operational in the Arctic, and it's 10 years past its lifetime, We had two, but that second ship, in fact, is being the parts from that ship are being used to keep the first ship alive. We have two other icebreaker ships, bringing the U.S. total to three. If you look currently at the numbers of other countries with icebreaker ships, you have Russia has 46 icebreaker ships with 15 more on the way, and China has 3 with 1 more on the way. So the upshot of that is that the changing Arctic conditions, we have these significant opportunities, but they also come with significant challenges. And the decisions we make today are going to shape the future for the next 50 years, potentially beyond. So, and in fact, all of us then on the call today really have a role in this, in being able to provide a better understanding of the Arctic system in order to, through better data, better models, and better process understanding, so we can get better weather predictions, better climate projections, and understand how these changes are influencing the fisheries and the ecosystems in the region. So in closing, I'd like to say that the Arctic is a unique region, and it has unique challenges. The inaccessibility of the Arctic has made it difficult for us to sustain high-quality observations, the observations required to improve our models. But despite these challenges, our scientific knowledge, and this is an example that this is shown in the chapter in the report, our scientific knowledge is sufficiently advanced to effectively inform policy. We've made significant progress of the knowledge of how and why the Arctic and Alaskan climate has changed and how it will continue to change. The Arctic is extremely vulnerable to rapid change. I think that's been made clear using just the observations over the last 35 or so years, but also using the model simulations going forward. And this makes the Arctic a key indicator for global climate change as well. Arctic inhabitants are on the front lines of climate change. And in many cases, they only need to look out their window to see the dramatic changes that are happening. However, these observed and projected changes are not just affecting the lives of people in the Arctic, but they have consequences for natural and human systems globally. I know this is maybe a bit overused phrase, but what happens in the Arctic doesn't stay in the Arctic. And I use this phrase, though, not because of the potentially controversial links between Arctic climate change and mid-latitude extreme weather, but because, from a physical climate system perspective, the changes that are happening in the Arctic are altering our global energy budget, global sea level, as well as the carbon cycle. And so certainly what happens in the Arctic is affecting the global climate as well. This is an important message, I think, takeaway, and it may seem obvious to us as scientists, but it's certainly not obvious to the public, and it's a question I hear frequently when I give public talks, which is, why do I care about the Arctic? It's so far away, it doesn't affect me. Well, it's like throwing a rock in a pond. Arctic climate change has ripple effects with the global reach. And what we've seen over the Arctic, the changes we've seen in the Arctic over the last 30 years, and our expectations are that these continue. But all the signs that we're getting is that the biggest and fastest changes may in fact lie ahead. So with that, I'll end. Thank you.
Great. Thank you so much, Patrick, for a great presentation. So we already have a couple questions on the chat. Phil asked in an earlier, can you see the chat?
In a minute, I can see the chat. I can now, I think.
Okay, so Phil asked about an earlier graphic. Is the volume of sea ice the modeled biomass figures?
So I didn't show anything with I didn't show any graphs with the volume. What was shown there is the age of the sea ice was shown. That's from satellite data. That's retrieved from satellite data.
Okay.
So but the volume that I speak of is from the biomass data set. Yes.
So is that modeled, or?
It is a simulation, so it's a combination of model and observations.
Okay, thanks. And then Tim Mock asks, to what extent is Arctic thaw causing the recent transition in the greenhouse gas radiant forcing increase from quasi-linear to quasi-exponential, based on AGU trailing average graph circulated late 2017 by Jim Henson?
Well, I guess I haven't seen that graph, and so I would hate to comment. So I'm not sure. So I would prefer not to comment on that.
Okay. Are there other questions? You can type your question into the chat box. That would probably be best because we get a lot of noise when we open up the speakers. Okay, we've got some questions coming in.
Sure.
I thought we did. While we're waiting for the questions, folks, Katie's included a lot of the links to where the recording and PDF will be, and also to the chapter. And so if you have any other questions, we'll have that recording and PDF up in a few days. The questions are still being typed, so stand by. Also, while we're waiting, I'll just point out that next week's talk on August 23rd is Tiding of the Tides by Billy Sweet, an oceanographer here at NOAA. So we hope you can join us. So are there any more questions? I thought I saw some and then people dropped off. Well, I have a question while we're waiting, if you don't mind.
Sure.
Patrick, can you describe a little bit more about the mid-Atlantic circulation patterns that affect the Arctic?
Sure. So the big thing about the Arctic is, about the influences, the connections between the mid-latitudes and the Arctic would be the jet stream or the storm track. How those fast-moving winds in the jet stream are bringing moisture into the Arctic. And one of the most favored places, as was kind of shown on that one slide of mine, is one of the most favored places for warm, moist air to be injected into the Arctic is through the North Atlantic region. And so, in particular, you know, the changes in the storm track in those regions will have a big impact on how much heat and moisture gets put in the Arctic, not just the location, but also the strength of it, whether the jet stream becomes wavier or not. And that ties back to some other oscillations that we know about, such as the Arctic oscillation and the Arctic dipole oscillation, which influence, you know, the storm track itself and how frequently air gets injected into the Arctic. But really, it kind of all comes back to the storm track variability and what controls that.
Okay, thank you. And then guest number 8 asks, I was looking for the temperature animation that has the link to Weather Network, but they cite Climate Analyzer and I can't find the animation. Can you include the link here or when you post the talk? Thanks, this was great, and I look forward to using this info in my class in the fall.
Yes, I can do that. I can find that link.
Great, thank you. And then Kim Gottwalls asks, can you confirm the #1 driver for Arctic amplification? An increase in downward LW radiation is caused by winds blowing warm, moist air into the Arctic?
So I can't confirm. So what I can say is that if you look across the climate models, and if you look across the recent analysis of the changes in downward long wave radiation, is that there's a very strong correspondence between increases in downwelling long wave radiation and surface temperature changes. And so I could say that the atmosphere itself is driving more energy, emitting more energy down to the surface, which is helping to warm the Arctic. Now, whether that's happening just because of the winds blowing more warm air into the Arctic is up in the air. And so both the melting of sea ice and the increased evaporation off of the Arctic Ocean that we've observed in fall and winter time, that's also contributing to an increase in downward long-wave radiation, as well as the winds transporting more warm moist air into the Arctic. However, so there's much more solid evidence, I would say, for the change in the increased evaporation driving these changes in downward long radiation and warming the Arctic. than the kind of the remote mechanism or the winds blowing it, because the atmosphere is very dynamic, and which means there's lots of internal variability. And so we haven't no trend, as far as I'm aware, no trend in the changes in the winds, the amount of warm air that's being transported in the Arctic have really risen above the noise. And so we're still, it's still an open question as to whether the changes that we've seen in recent years, where we've had these big events of heat transport into the Arctic driving much warmer temperatures, it's possible that these are driven by internal variability and not driven strictly by force changes or in response to CO2 forcing. And so that's where, why I wouldn't be able to confirm that that the heat transport is the number one driver, because both of those mechanisms that I discussed are really contributing to the increase in downwind long-wave radiation.
Okay. Then Gabrielle Roche McNally asks, were any Arctic tribes involved in the public comments for your chapter, and what kind of responses are they giving in response to this chapter?
So from what my memory, for what I remember for answering all the comments, is there were no comments from the Arctic tribes, and I also haven't heard any specific responses from the Arctic tribes to this chapter. However, I was in attendance at COP21 and did get to talk to several folks in Paris from Arctic tribes, and they are supportive of the science that we're doing and saying, and they are willing to share lots of anecdotes about specifics about how the changes in sea ice are affecting them. And so I haven't heard any specific comments or responses from the Arctic tribes about the chapter itself, though.
Okay. And then Chris Holderreed asks, do we know what drives the variability in the model scenarios for the Arctic, for example, parameterizations?
Yeah, so, this is certainly an open question as well, but primarily it is, yes, the physics or the parameterizations in the model. Whether the specific parameterization that's maybe most at fault that's something that's up in the air that we're not sure about. In my research, I'm focusing specifically on the cloud parameterizations, specifically the cloud phase, meaning how much of these clouds are made up of supercooled liquid versus ice, because the supercooled liquid clouds tend to have a stronger warming effect on the surface than ice clouds. And so some of these climate models have, and there was a paper by Tan et al., Ivy Tan et al. A few years ago in Nature showing that climate models that with larger amounts of supercooled liquid, in fact, do warm the Arctic more. And so the clouds are definitely a big piece, but there are also things that we don't quite understand about boundary layer dynamics in the Arctic, and also about how all these things influence the sea ice and the sea ice processes as well. So certainly it's the parameterizations, and I'm guessing that all of the parameterizations can shoulder some blame in this.
Okay, and then Susan Walker asks, generally, why is the Arctic amplification not as dramatic in the Antarctic?
So there are a few reasons why this is the case. And so the Antarctic is clearly not warming quite as fast at all as the Arctic is. One of the reasons is that in this case, in the Arctic we have an ocean that's covered in sea ice that is surrounded by land, and so this gets the situation where we have a lot more sea ice in the central region, and this promotes a stronger ice albedo feedback than what we've seen over Antarctica. So the fact that Antarctica has this continent in the middle with sea ice around it versus the opposite, so that kind of geography is different and contributes to part of it. The dynamics of the atmosphere, partly because of that, but the atmospheric circulations and the storm track is also very different in the Arctic and Antarctic. The Antarctic generally has this, the polar jet stream, the jet stream storm track there is essentially a very, I guess a concentric, it's a ring that's very tight. It's stronger. It's not as wavy. Let's put it that way. The storm track in the southern hemisphere is not as wavy as the storm track in the northern hemisphere, and that is in part because of the lack of continents, right? In the northern hemisphere, we have many more continents, which help make the jet stream wavier, and it's part of the reason why we see storms in the places that we do, specifically the east coast of the U.S. And so partly that the dynamics of the situation are also important. And also there was this came up during the writing of the chapter. There was a paper that came out a few years ago to try to understand why Antarctic sea ice for several years there was actually increasing and not decreasing. So we had an increase in Antarctic sea ice for some years. And this seems to be, it's hypothesized that this is related to the ocean and some circulation link between the tropics and Arctic that was actually helping to slow the sea ice. And so there's other potential natural variability, other potential oscillations in the climate system that were kind of influencing why we haven't seen quite as large of a change in the Antarctic as we've seen in the Arctic.
Okay. Time for one more question, Patrick?
Okay, sure, yeah.
Okay. Katie Hagman asks, have there been studies on how a new fire regime in Alaska will mean for ice melt in Greenland?
So I'm not familiar with a study that specifically links those two. However, there's certainly been studies on looking at the potential influence of fires and pollution and black carbon being deposited on the ice, and the potential for that to darken the ice and therefore make it absorb more solar radiation and accelerate the melt. And so that's definitely something that has been looked at in recently, and so that's definitely a process that we've that is under study. However, there's the exact rate, how much that might be amplifying the melt is uncertain. But there certainly is, especially around the edges of the ice sheet, definitely is a darkening of the ice sheet is happening, is observed there, where the albedos of the ice sheet are definitely less. And so again, there haven't been studies that I know of that link this new fire regime to Alaska and what that means for the ice melt, but certainly people are looking at what pollution and what fires depositing the pollution onto the ice means for the ice albedo and potential for the future of the ice sheet.
Okay. Well, that's about all the time we have and all the questions we have. So, Patrick, thank you so much for presenting today. It's been a terrific look into the Arctic. And folks online, you probably saw his email if you have questions. Or if you don't have it, you can email Tracy or Katie or myself and we'll send it to you. And Katie, again, has posted the recording, link to where the recording in PDF will be up in a few days. Well, any last words, Patrick?
No, I appreciate the opportunity, and I hope you enjoy the presentation and now feel that living here, most of us, I assume, living farther south of the Arctic, that you feel a bit more connected to the Arctic now, because it does impact our lives and the future of the U.S. and the world going forward. So we're much more connected to the Arctic than we think on a daily basis.
Well, thank you. Katie, any last words? Okay. Well, thanks everybody for... Oh, go ahead, Katie.
Thank you so much for joining us, everyone.
Okay, we'll see you next week on August 23rd for Tidings of the Tides. Thanks again, Patrick. Bye-bye, everybody.